Okay, so this is the last module of last set of lectures this quarter. So let's do a recap of logic. So what have we talked about? So we talked about logic during this week. We talked about three main ingredients of logic. We talked about syntax, which basically defines a set of formulas, allows us to syntactically, symbolically talk about formulas and talk about things that exist in the world. So for example, I might say rain and wet without knowing what rain means or wet means or what this and symbol means. And that is in the syntax land where I just like have symbols and I can manipulate those symbols. And then I can assign meanings to the syntax using semantics. So the idea of semantics is that for every formula, we can specify a set of models, M of F, which is basically a set of assignments or configurations in the world that assign meaning to a formula, a syntactic formula F. So in the case of rain and wet, for example, rain can take values 0 and 1, when wet can take values 0 and 1. And then in the case of rain and wet, it would be this darker area that corresponds to the meaning of what does it mean when both rain and wet is true. Okay. So in general, when we try to define logic, we need both syntax and semantics. Syntax as a symbol, as a way of just writing out the formula, semantics as a way of giving meaning to those formulas. And in addition to syntax and semantics, we talked about inference rules. We spent quite a bit of time talking about modus ponens and resolution for both propositional logic and first order logic as ways of doing inference on our knowledge base. So we have a knowledge base which has a bunch of formulas. And the question is, what are some new formulas that we can derive from that knowledge base? For example, you might have rain and wet. And from that, I can derive rain, right? Like I can actually derive and prove that it's raining. So how do we think about inference rules? How can we infer new type of formulas here? And what can we tell about the formulas that we infer? So I think that is also an interesting question that we have been talking about. So how do we think about inference algorithms? So if we have a knowledge base, the idea is if we have an inference rule, like modus ponens or resolution, we should repeatedly apply that inference rule until we get new formulas and we derive new formulas, new F. And as we get new formulas, you're expanding our knowledge base, but we're shrinking the space of models because we're adding more constraints. If I add a new formula, in general, I'm shrinking my space. If I'm deriving a formula, though, if that formula is just derived from knowledge base, so it's not changing the size of my knowledge base. So here's an example. So let's say I have wet and weekday implying traffic. From these three formulas in my premise, what can I conclude? What can I infer? So we talked about modus ponens as an inference rule that allows us to infer traffic out of this. Okay. And then more generally, what does modus ponens does? What does modus ponens do? Modus ponens thinks about having a set of propositional symbols, P1 through Pk, and then a formula that is P1 and it through Pk implying Q. And then it basically says we can derive Q. That is what modus ponens does. And then we basically talked about soundness and completeness of inference rules. For example, modus ponens as an example. So what does soundness mean? Soundness means that if you're deriving things, if you're deriving new formulas, we need to make sure that these new formulas are actually true. They live in this space of things that are entailed and are actually true. And if you remember our example with glass and water inside of the glass, what soundness means is anything that we are deriving should be inside of the glass. It should be a formula that's inside of the glass because everything that's in glass is entailed and is true. So we need to make sure that everything that we're deriving, if you want to make sure it's sound, it has to be inside of the glass. On the other hand, we talked about completeness. And completeness means that we are deriving the whole truth. Meaning that if I have this glass, I should be able to derive everything that is inside of this glass or even more. That is what completeness means. And if I have both soundness and completeness, then derivation and entailment are basically the same thing, right? Like remember, entailment is about meanings, about semantics, right? Entailment is about what is the meaning of F actually being entailed by the knowledge base or being contradicted by the knowledge base. But derivation is just basically symbol manipulation. Okay, so it's difficult to talk about entailment kind of in the semantics land because you have to think about meanings and so on. But if you can do derivation in the world of syntax, you're just moving around formulas and kind of mindlessly by moving around formulas and applying inference rules, you can derive new formulas. And that allows you to have a compact way of thinking about these formulas and new formulas that are being derived. So if derivation is the same thing as entailment, that's pretty nice, because if you have a virtual assistant and you want to ask your virtual assistant a question, or maybe you want to tell it some information, that corresponds to maybe an entailment question, and that might be difficult to answer. So instead, if you have a sound and complete inference rule for your logic, then maybe you can just check derivation, and derivation alone is going to give you the answer. Okay, so that is why we talked about derivation for a bit. And we discussed modus ponens for propositional logic, and the fact that modus ponens is actually sound for propositional logic, but it is not complete. It's not able to get all the formulas that are true. So in order to solve that, we had two solutions. One was maybe propositional logic is too large. Maybe we should reduce the size of propositional logic. And then the other idea was maybe modus ponens is not as strong. Maybe we should make modus ponens stronger, or come up with a stronger inference rule. So let's talk about those two ideas. The first idea is propositional logic allows us to talk about any legal combination of symbols. And that is pretty expressive, but maybe that is too expressive. So maybe we can just look at propositional logic with only horn clauses. So this is a restricted set of logic formulas, and that allows us to basically have this more restricted set, and that allows us to get both soundness and completeness with modus ponens. So what is a horn clause? Horn clause is basically a clause that has at most one positive literal. So if you write this in the CNF form, in the conjunctive normal form, then you want to basically make sure that you have at most one positive literal. Another way of writing it is that you have an AND of a set of propositional symbols, P1 ANDed through PK, and that implies some Q. And you basically want to make sure that there are no ors here, or no branchings here. That is why we could actually show completeness with horn clauses. All right, so that was basically propositional logic with horn clauses using modus ponens, and that gives us completeness. Okay, without the general propositional logic doesn't give us completeness with modus ponens. The other option we discussed is maybe we should have a fancier inference rule. Specifically, resolution was the thing that we started looking at. So resolution was able to give us both soundness and completeness. The issue with it was it was actually exponential time as opposed to linear time when we think about modus ponens, where we keep adding only one formula, and at most we'll end up with n formulas. But with resolution, we might have an exponential time algorithm. But we end up getting both soundness and completeness, which is nice. Okay, so that was all about propositional logic. At some point, we started talking about first order logic. So we started expanding our logic and tried to be more expressive in our logic, tried to be able to talk about variables, talk about quantifiers, and be able to have a better way of representing things that are much harder to represent in propositional logic. And then we started talking about syntax, semantics, and inference rules for first order logic. So basically we went over the same things for first order logic. So comparing propositional logic with first order logic, in propositional logic, we have this option of doing model checking when we think about our models and the semantics of our models. In first order logic, we don't really have an analog of that, but we have this other thing called propositionalization. So for a subset of first order logic formulas, what we can do is we can do propositionalization, and that takes us back to the propositional logic land, and we can use the same tools that are there. Thinking about inference rules, we discussed modus ponens with horn clauses and the fact that it's sound and complete. Same story is true with first order logic. So we could apply modus ponens with horn clauses in first order logic. It's sound and complete. There's a plus plus here, and that plus plus basically means that we had to change modus ponens a little bit. So we discussed unification and substitution because we have variables here. So because there are those variables, we should be able to, we should apply unification and substitution to make sure that our modus ponens make sense in the space of first order logic. Similarly, we discussed resolution, and it showed that it is general and it's sound and complete in propositional logic. And in the case of first order logic, we briefly discussed this in an optional module. And again, like this is resolution plus plus because we are talking about applying unification and substitution on resolution too. And again, it's sound and complete even under first order logic, which is kind of nice. All right, so that summarizes our logic lecture. I just want to leave you guys with one thought when you think about logic. So what is it about logic that is useful again? We talked about all the limitations of it, right? The fact that it can't handle uncertainty, or it's not probabilistic really, or it's pretty brittle. It's not able to capture data. As you get more data, it's hard to update its rules because it has all these deterministic rules that are built on top of each other. But it does have one big benefit. And that one big benefit is that it allows us to have a very compact and concise way of representing knowledge that we wouldn't normally have, right? Like, remember, like, the whole point of inference rules was I have this logical formula, which is like a very compact way of thinking about semantics and knowledge that's actually pretty difficult to represent in the semantics land. And now that I have this concise formula, I can just manipulate it. I can move it around, and I can do all sorts of inference rules on top of it. I can come up with new formulas, derive new formulas, and prove new formulas. And that's pretty interesting. And it's much harder to do that in the semantics land. So the thing that logic really gives us, it's really like big strength here, is having this compact representation that can help us think better about formulas and do better manipulation of them. And I think one thing that would be very interesting to think about is how could we use these ideas, maybe not exactly logic, but ideas from logic in some of the more modern AI systems, some of the more modern machine learning based systems. And I think that is a pretty interesting view of logic that would be good to take from this class.